This is very important. I think many students are waiting for the recorded video. Right. I think some students they'll join us later. I think we have to start right now, otherwise we'll run out of time. All right. Any problem with your assignment? You can let me know now. If we have time, we're going to go through your assignment today. After the short introduction of each tutorial. So if you have any question you want to ask me, you can ask me now regarding your assignment. I'm not sure whether you have already submitted your assignment 1 or not, but you still have time to do it if you haven't done so. You still have time to do your assignment 1. Usually our CC will allow you to submit a bit late after the due date, so you don't have to worry too much about your assignment number 1. So we have question 1. I think it's quite okay. Question 2 is regarding you need a few equations. I think we haven't covered question number 4. Question number 4 is a Norton theorem. Hey, did we cover in our lab? I think we covered in our lab already, right? On Norton theorem. I think Norton theorem we start at the Thevenin equivalent circuit. Okay, we have 2 students coming in. And RBA from KL, welcome. From KL. RBA must be here, right? Rajib bin Amirullah. Okay. I hope I'm right about this RBA. So if you want to confirm, you have to type your name here. Okay, you have to type your name here. At this chat box here. All right, let's go straight to where we left previously. Previously, we have completed part of tutorial 2. We only cover a partial half only on the tutorial 1. Okay, so I won't repeat again because we run out of time. We have a limited time here. I won't repeat the initial part of tutorial 2. So tutorial 2 is about the first part here is about the nodal analysis. So we based on the node here, example the V1 here, and then we start working out some of the current case using the KCL. Because the KCL is focused on the node, so we're starting from here. I1 in, this big I1 in, small I1 out, small I2 out, okay, and the big I2 out, okay. So we can write this kind of equation by using the KCL based on the node, okay. This one is called the nodal analysis. Another one after this nodal analysis, we have another one called the mesh analysis. So the mesh analysis basically using the KVL because it sum all the voltages around a loop. Okay, a loop. Sometimes they call it mesh also, a mesh. A loop here. So here apparently we have 2 loops here. Where 2 loops we can sum up all the voltages just like this one, I1 and I2. Okay. Okay, we have this I1 and I2. You can sum all the voltages. Usually I'll start from the V1. You see that start from this end here. You can see the negative end here. We go from left to the right. So you on the left you can see the negative sign. So you can see the minus V1, and then this one we assume here is a plus. So plus R2 plus R3, and so on. And then we can quickly write the first equation here, plus V1 plus VR1 plus VR2, and sum all the voltages must be equal to 0. Okay, so and later on we can use the Ohm's law to convert the R1 to I1 R1 and so on. And then the rest is just the algebra. You just work on using the calculus you learned in the calculus class and find all the unknowns. So we can say that the nodal analysis and the mesh analysis, they are based on the KCL and KVL. All you need to do is just to come up the equation and then find the unknowns. All right. And now we're back to here. I think we in our first previous lab session we touched this Thevenin theorem. Okay, Everton here. Okay, later I'll mark the attendance. Okay. You mean RBA is Everton? Cannot be, right? Right. Okay. I think he's not joining us, right? He only I think he need to click the meeting icon. Because I know that some students, they have no experience in this MS Team. I think it's still outside. This student Everton is still outside because we can't see his name here. How do I approach him? Is this Everton? Let me copy this. Okay, so I mark your attendance just now. Rajiv, right? Rajiv. Okay. So sometimes the student, they're learning outside the page here. Sometimes the student, they're learning here, they don't know how to join here. Let me get this student. This is a problem with the online classroom. Sometimes not all the students have experience with this classroom here. They need to click on this icon, not just reading this text here. Oh, it's Mahav of Raji from Ipoh. I think he's in also, right? He's in also. Let me see. But how come I can see only 2 students here? Oh, got 2 students. Stranger? Are they? The screen I'm seeing is different. Ipoh. Yeah, it's correct. Tutorial 2. How come they didn't see the screen? Strange. Let me log in again. Let me log in again. I need to share the screen again. Sometimes we have this problem. Let me manually ask them to join. From Ipoh, M something. Mafuraji from Ipoh. Let me check. I don't think so. No M. Not. I think it's from here. MS4, right? I think he has some problem with his platform, I think. I think there's still a problem signing in. So far, we have 3 students here. Actually, we should have more than 3. So for those who are here, can you please type your name here so that I can? And then this student, Edward Stan, he managed to type in here, but he's not here in the meeting room. So I'm not sure whether he knows how to join or not. Sometimes we cannot just stay here forever. We need to continue our class. So I think we'll come back later. Okay. I think they can watch the recorded video. Okay, when in the last lab session we actually conduct a test on this Thevenin theorem. So basically, for most of the circuit we have, actually we have some circuit, we call it a fixed circuit, and then we have a variable circuit. A variable circuit is the one that the user actually they attach their load, example their lamp or something, or their speaker. So their speaker is a different speaker, right? But the circuit is the same. Let's say this is an amplifier. So the amplifier circuit is a fixed one, but the speaker, you can use a different size of speaker. So the speakers we consider as a variable kind of part. So we can actually find the resistance and voltage for this fixed part of circuit, and then we can later on join with the variable circuit. We can calculate easily calculate the currents and the voltage, because after we reduce the whole circuit here to only 2 components, V and R. Okay, if we know these 2, of course we will know the current. Current is the V divided by R. So after we have successfully reduced this complex fixed circuit to a really simple 2 component only, and then later on we can use this one to analyze our load based on a different load. So to do this, you need to follow a few steps actually. First, you need to assume that you need to take out the voltages. Okay, the first step is to take the voltage source out. Okay, take this one out and replace with a short wire. So what you see here now is all the resistance. Then we use our circuit analysis to reduce this resistance to only one value. We find something we call the equivalent resistance of the whole circuit. Okay, but another name is called the Thevenin resistance. Okay, this one is used as, because some components here is parallel, some components is in series. So we work out the equivalent resistance And then for the second part here, for the second part, we remove the first part is to remove the voltage source, remove the load, and then become open circuit, turn off the source, turn off the source, and with a short circuit. Okay, remaining unchanged as a dependent source need external source to be activated after supply second step. The circuit becomes dead circuit. Okay, so just follow the step here. First, remove the external source, then remove this one, replace with a short wire. But this one, the example here is go ahead and calculate the mesh 1 and mesh 2 here. Okay, you can read this on by yourself. So if you encounter any problem, you can talk to me again. How come? How come they cannot join here? I don't know how to help. So let me send a message to them. Hello, can you click on the red camera icon here? I mark with a circle here. You click on this icon, you can see the meeting room. Quite loud actually. Okay, so Thevenin and then you have Norton. So Norton is a different thing. Norton reduce the circuit, the fixed part of circuit into the current and the resistance, but in parallel. If you compare with the Thevenin is not parallel. Thevenin is in the series circuit, right? They are all in series. Like this. Oh, they didn't show the. Here should be a Thevenin voltage, right? Thevenin voltage. Yeah, Thevenin voltage in series, right? These two are in series. When compared to Norton, there are two different methods actually, but they're doing perform the same function, which is to reduce the circuit into two components. So this one reduced to Norton current and the Norton resistance, but in parallel. So the step is quite similar. First is to find a short circuit of terminal AB. First is short the output here, and then it's trying to find the current IC. Okay, like this, and then at the end you have the two components. You find these two components, then you just attach the A and B to the load. You can calculate the output currents. Okay, here's the example. First, you see this part. You take away this current source here. Take away the current source, then become open, and then take away the voltage source, and become the short circuit. So the first part is to calculate the total resistance, just like the Norton theorem, just like the Thevenin theorem. Okay, voltage source is replaced by a short circuit, current source become open circuit here, so we can ignore this part here. We just focus on these four components. So we slowly using the circuit analysis technique. We reduce these four resistance into 4 ohm. Okay, later on we use the circuit analysis to find the currents. We kind of find the short circuit current here. We put everything in here. Okay, then we find the short circuit currents. Short circuit current is a Norton current, right? Okay. So after that, you can find many examples online. Let me see here. Yeah, I think he's in already. Okay. Okay. For this Norton and Thevenin theorem, you can easily find many examples on the YouTube. On YouTube and on other websites, there are many tutorials out there. So it's not a problem. Basically, all you need to know is that these two theorems is to help you reduce the circuit, okay? So that later on you can analyze the circuit easily after you attach the external component. So the most important thing you should remember, because from my experience, sometimes I realize that most students they have no idea what is the purpose of learning all this Norton theorem. So let me try to explain you one more time here. Let's say you have a really complex circuit here. You have a really complex circuit with a lot of resistance. Okay, really complex circuit here. And then this circuit will be attached to the external load. You have one external load, sometimes a speaker, as a speaker example. You attach this load here to the circuit. Okay, and then this circuit try to power this load, right? Okay, but if you try to analyze the whole circuit here, including every components, become really complicated, right? If you want to calculate the current passing through the load here, the RL, sometimes most of the time we call it RL. If you try to find the current of this RL, you need to analyze all the circuit here. So this is quite troublesome. It's a really time-consuming kind of things. So if you reduce this one to only two components, one is the voltage, and then the other one is a resistance. And then this point, these 2 points, we call A and B, same point. After you have reduced the whole circuit here into only two components, V and R. When you attach another component here, it's really easy to calculate, right? You can see now this resistance is in series with this resistance. So the current here, the current now flowing through the RL is equal to V over R, right? So the V is a VTH, and then the R is our RL plus RTH. Okay, because these two are in series. So it's really easy to calculate this current if we can reduce the whole circuit here into two components. So this is the purpose of learning these theorems here. And after you calculate the I, then you can calculate the power. The power flow through the RL. The power flow through the load here will be you can using this equation here, I square R. So I is RL, of course. This is RL. Okay, if you by knowing this IRL flowing through this R, we can calculate the power. Another equation you can use is a V square over R. But the V square here is not here. It's not this voltage. It's the voltage across this RL. It's a VRL. The VRL here. Another one is the I times R. RL. I times RL. I is IRL here. Okay, so we have three equations we can use to calculate the power of this. Sometimes we call this one the external load. This is the fixed circuit. Here is the external load. Okay, that's why we need to learn these two theorems. So as you know, you can actually find a lot of example online. So I won't actually worry about this right now. Okay, the last topic here is called the well, this is still not last topic. I think the next really short topic here is called the maximum power transfer. So the maximum power transfer is try to calculate what resistance should you use to achieve the maximum power output. How to achieve the maximum power output? For example, let's say your circuit here. You have one voltage source as your power source here, and then you have one internal resistance here, like the battery. You know, most of the battery we use in our car, even though the battery function like the voltage source, right? But actually inside the battery we have kind of something we call the in series resistance. So this internal resistance here inside the battery is already come with the battery, always come with the battery. So if you want to attach 1 R here, your external load, like your lamp of your car, the headlights of your car. So your headlight is some kind of R, right? Some kind of RL. So if you want to achieve the maximum power output, your power output, you want to have the maximum output from this power source here, your R must be equal to L. To achieve the maximum power output, your RL must be equal to Rin. Okay. Example, let's say here is a 5 ohm. Okay. So your RL must be 5 ohm also, if you want to achieve the maximum power. All this can be proved by using all this equation here. Your RL must equal to your R Thevenin. In short, your load must be equal to this for the maximum power transfer. Another good example is like this. Let's say you got one amplifier. I'm talking about the car amplifier. Let's say you got one signal here. Okay, after amplified by the amplifier, we got this amplified signal, AC signal, and in the amplifier also come with some kind of internal resistance, Rin. Example 4 ohm. So you after the output here, you will need to connect to your external speaker to hear the amplified music, right? You know when you're choosing the speaker, you can choose a 4 ohm, 8 ohm, 60 ohm, or 32 ohm, right? Usually the headphone they're using the 32 ohm, right? Using a really large speaker, they're using a 4 ohm or 8 ohm. So in order to achieve the maximum output from this signal here, from this amplified audio signal, if you know the internal is 4 ohm, then you should choose a 4 ohm speaker here attached to the output to achieve the maximum output, so that you can hear the loudest output from the speaker. This is the practical things if you want to know that why we need to learn all this maximum output count theory, maximum power transfer. That means your output resistance must be equal to your Thevenin resistance. I think this one is in your assignment also. Let me have a quick look. I think this one is in the usually is in the assignment also. But not this time. I think in assignment 2. Let me see assignment 2. Let me see, is it in your assignment 2? Because usually I remember all this, they will have this one question for this maximum power transfer. Let me make sure it's correct or not. Let me find where is it. Not in this semester. This semester is not in the assignment. But for previous semester, is one of your assignment question, maximum power transfer. No, not here. So none of the question come from this maximum power transfer. So you don't have to worry too much actually. For this semester, your final answer will be replaced by the assignment number 3. So you'll be given about 2 weeks time for you to complete the assignment 3. You can take your time at home to come up with the answer. So when the time comes, I think we'll look at this again, maximum power transfer. Okay. So the next topic here, I think should be the last topic, right? It's called a superposition. So what is this about? It's another theorem to help you analyze the circuit actually. Okay, so this superposition, there are two independent sources here. We have one voltage source and one current source here. Okay, to find the superposition, use the superposition to find the voltage V here, the voltage across the resistance. First, we need to assume let the V equal to V1 plus V2. V1 plus V2 here. This is V1, here's plus V2, right? So we let V, then we find the first we use the KVL to find all the voltages in a loop here, -6 plus this one, right? And then slowly we work out the V1 here. Hey, wait a minute. This doesn't explain the superposition, right? We have two independent source, then we determine the voltage across either by voltage 1, we denote as V1. Then we determine the voltage across V. Okay. So basically, he just removed because in this circuit here, we have two independent source. First, we deactivate this one. We remove this one, and then we find the voltage V1, and then we deactivate the other one. We find the voltage V2, and then we sum these two voltage. We can get the voltage V. Okay, we only activate one independent source at a time. So for this example here, we deactivate this current source here, and then we find the loop, and then we find a V1. Okay, and then for the next step is not shown here. The next step we deactivate the voltage source. Okay, we only have the current source here. We deactivate this source, and then we try to find the V2 here, and then at the end V1 plus V2 is our V, is our answer. So he didn't, this slide, he didn't show the full solution. This is only part of the solution only. Okay. This equation, I think when you first, never mind. I think you can read through. I think the best thing for you to do is to read through the notes here. And some students, they also don't know where to get the notes. Actually, the notes for this unit 2, you need to come to this facts learn here. Okay, you come to this. We have two main lecture notes here. One is the PowerPoint, one is the PDF file. The more complete version should be the PDF file. So you need to download, click and download this file to your PC. And then you really need to take some time to go through all these notes here. Okay, I think the notes will explain in detail. The notes will explain in detail the superposition. 69. Let's go to 69. Now, do one voltage source, one current source. We want to find the voltage here. V1 to 4V1. Okay, then take away this one. Take away this one. And then we keep the current source here. We find the V2 here. So the V2 is 8 ohm, 8 volt. Just now we find the V1 is a 2 volt, and then we find the V2 is 8 volt. And then at the end, 2 plus 8, we get a 10 volt is our answer. So sometimes it only happens when you encounter the circuit like this. We have two independent voltage source. This one is not depend on this one. You have to understand. There must be independent. Independent means this source is not depend on this one. So how do you know this is depend on this one? When you see something like this, when you see something like example. Let's say here we call the V1. Okay, let's say here is called V1. And then later on in other circuit here, let's say you have another source here is called a 6V1. That means this source here is depend on this. Is 6 times the V1. So if here the voltage change, here also change, right? Because this one is 6 times the V1 here. So this is called a dependent, right? They call the dependent source, right? But we come to here, this example, they are totally independent, right? One is the supply the 3N, one supply the 6 volt. So they are considered independent source. In this scenario, then you can use the superposition theorem. But for my experience, the chances of using this superposition theorem is really low. Usually we just use the KCL and KVL. I think 90% of the time, we just use the KCL, KVL. We can solve the circuit analysis, task. We don't need to use this superposition, but this is just one of the theorems you should know. Okay, it's good to know this theorem. And then we come to this voltage and current divider. I think this should be the last topic. Basically, this current and the voltage divider, I think I can explain it in another easier way to explain this one. Let's say you have one voltage source here. Okay, let's say it's a 10 volt. 10 volts is easy to it's a good number to calculate, right? So let's say you have 3 resistors here. But let's start with 2 resistors only. Let's say you have only 2 resistors. One is a 9K. One is the 1K. So the two of them just add up to the 10 volt exactly. So you can say that 9K, because of the more resistance, will take more of the voltage out of this voltage source. So when you measure it, you should get a 9 volt here. And then you should get only 1 volt across these two points here. Okay, so if you name this one as a V1, this one V2, this one V3. So V3 minus V2, you get 1 volt only. V2 minus V1. Oh, sorry, V1 minus V2, you get 9 volt. Okay, V2 minus V3, you get 1 volt. Okay, this is a voltage divider. So we treat this one as these two resistance, they can divide the voltage actually. So sometimes what we use in the real world, we just use this one to get the the partial voltage. Example, let's say here we want to get only a 0.1 volt. So 0.1 volt is a 100 out of this, right? It's a 100 times 10, you get 0.1, right? So here we should use a 99K. Here just use 1K, right? So it's 1 over 100. So after this, the voltage drop here, it dropped 9.9 volt here, and then we have only 1 volt, 0.1 volt out from here, output. So here's ground. Okay, so between this node and this node, we have only 0.1 volt here. Basically, usually this is replaced by the something we call the variable resistor. You see something like this. In the real world, we're going to use something like this, something we call the variable resistor. So this variable resistor is a 3-point kind of a component. So we have this one terminal, 2 terminal, and another 3rd terminal here, 1, 2, and 3. So this one, it can be adjusted. You can adjust this one to the far right and the far left here, to the left and the right, to adjust the portion, the ratio between the. So if it adjust here, that means 0, right? If it adjust here is a full resistance here. So from here we can use it as the voltage divider. We can divide the voltage into 1 over 9, 1:9 ratio, right? 1:9 ratio, and this one is the 1:99 ratio, right? So we can add, all this is called the voltage divider. When you come to the current divider, is a different story. When you come to the current divider, you cannot just divide the current like this, right? The current need to divide using the parallel. Let's say here we have 100 ampere coming in. So if we want to divide the current, we need to divide using the branch. So we have another resistor here, another resistor here. Okay. So if these two resistors are the same, example, let's say you have 1K here, 1K here, and this current was split to two. The first one pass through here, the other one pass through here. At the end, they are divided into 50 and 50, right? Because these two are the same. Okay. So when you look at the difference between this voltage and current divider, you can say that the voltage is using the series. The voltage divider using all in series. Just now my example using only 2 resistors, right? But here you can using many resistors to divide the voltage. Okay. When you come to the current, that means you need to using the parallel circuit to divide the currents. So this is the thing you should keep in mind. How to divide the current, how to divide the voltage, how to get the partial from the main voltage here. So we usually assume this is the main voltage. This is the largest power supply, the largest current for this circuit. And if you get a small current out of this measurement here, we can use the current divider. When it comes to practical circuit is when in which circuit we will see this current divider. Usually, you can see in many circuits, they are in the circuit to divide the current, to divide into smaller current actually. So they use this current divider circuit. You can see this in many ways actually. In many possible circuit, you will see this the current divider. When you see whenever you see two resistors in parallel, that means it's some kind of current divider already. Okay, so you will see this quite frequently in the circuit in the future. Sometimes we won't just purposely try to divide the current. Sometimes we divide the current because the circuit already got some internal resistance, and then the current will be divided by certain ratio based on the resistance here. You can see the current output for this IN here. For this IN is you need to take this resistance here G. Okay, G over all the resistance here, then multiplied by the main current here, the main current. All right, that's all for Unit 2. Now we should take our time to look at Unit 3. And then for those, okay, I think you type your name here. For those haven't submit your TMM1, actually you don't need to worry too much actually. Usually the CC will allow you give you opportunity to submit after the due date most of the time. Most of the time, but doesn't mean that this is our policy, right? This is actually not the WOU policy. But for my experience, every time after I mark the assignment, the CC sometimes they will ask me to talk to the student. Whoever not submitted yet, they can still submit the assignment. So it's something that you shouldn't worry about. If you are late for this assignment, you just take your time quickly complete it, and then you request to resubmit or something. Okay. And later on, with time, do you have any question for me? Do you have any question for me? If you, otherwise, I'll go straight into the Unit 3. And if we have time left, we'll go through each question individually. Okay, to help you with your assignment 1. For assignment 2, your due date is March. I remember it's the 3rd of March. Let me double confirm. Your assignment 2, the due date is 6th of March. Usually, assignment 1 they are quite loose actually. For assignment 1, they won't require you to submit on time, but for assignment 2, sometimes they are quite strict. So my advice to you is for your assignment 2, you try not to delay the submission. Okay, for assignment 1, you can see some students already submitted. So if you make some changes, you want to resubmit again, I think you can request for something we call the resubmission request. You see here we got one resubmission request, right? So after I give you all the hints about the assignment 1, if you want to make any amendment, make any changes, you go ahead and make the changes, and then you request for the resubmission. The reason is quite clear, because the due date for the assignment 1 is January 30th. At that time, we haven't complete the Unit 2 yet, so you have no time for you to prepare for the for some of the question. Some of the question come from Unit 2, like the nodal, not the nodal, the the Devlin question and Norton come from the Unit 2, and when the time the due date we haven't actually covered the this topic yet. That's why I say that it's a quite reasonable for you to request for resubmission after you complete this today's class. You can work on the Devlin. So I think I need to take some time to go through this one by one, but probably not now. Now we need to cover the Unit 3. I need to take a spare time, extra time to cover this individual question here. I want to give you some tips so that it won't you give some kind of direction to you, some kind of direction, so that you are quite sure that you are going the right way. Okay, so you don't have to worry too much right now. Actually, for those who have submitted, also they have a chance to resubmit again. Okay, we're going to make sure we're going to do this today. I think we cannot delay anymore. We need to make sure we have to quickly work on our assignment 1. For your assignment number 2, assignment number 2, last time we skipped question 1 and 2, as you know. Question 1 and question 2 are in the this one is in the Unit 4 actually. This one in Unit 4. So what I can help you before the 6th of March. Let me check. Before the 6th of March, do we actually have time for the Unit 3 or not? So the 20th of March, we need to. Wait a minute. 20 of February. 20 of February is our second lab, 6-hour kind of lab session. And then the next week, 1 week after, we got another session. This will be your Unit 3. So it's still before the 6th of March. Okay. In other words, for the assignment 2, we have sufficient time to cover the all the topics for the assignment number 2. Okay. Only for assignment 1 is a bit strange the way how they arrange it. Okay. Now back to our assignment 2 again. So assignment number 2, this comes from the Unit 2. This comes from Unit 3. Last lab we covered the question 3 and 4. I think we covered 3 and 4. Right? Noted here. We covered 3 and 4. And then the 4, 5, 6. Wait. 3 and 4. And then question 6 to question what was the last number? Question 6 to question 8. This should be the last one. The transformer. The transformer is question 7. Only 6 and 7. Okay, we'll cover those in the we're using a 6-hour. 6 hour means we need to cover 3 questions usually. 3 questions. I think it should be this one, right? Should be the Norton. Lab 3, yeah, Lab 3. So I recall the previous lab session we only cover Lab 1 and Lab 2. So Lab 3, Lab 4, Lab 5 will be done with this 6-hour. During this 6-hour lab here, 20th February. So make sure you attend this lab. Otherwise, I don't know how to help you to complete these 3 labs. Okay. For the rest of the tutorial, probably you can watch the video. But for this 6 hour, we can take the time to complete your assignment 2. Okay, complete your assignment number 2 so that you can get higher score for assignment number 2 usually. Let's say for assignment 1 you get about 70. I think for assignment 2 you definitely can get above 80 because I've provided you all the answer for the lab. You just need to follow the step by step. I show you the step by step. You just follow it, and then I think you can get really high score for your assignment number 2. So make sure you attend this lab number 2. Okay. I think we should take a break. I think because according to the government, they say for the online class, for every 30 minutes we should have about 5 to 10 minutes of break time for every 30 minutes. We cannot just go straight 2 hours without any stop. Okay, I think we take a short break here. Okay, guys, we take a short break here, and then later we'll come back. We go through this. We go through this unit 3. All right. Okay, I'm going to mark attendance now. Edward Tan from Ipoh. This is Rajiv KL. Okay. Abdin Bakam Ipoh. Ipoh KL Ipoh. Yeah. Kumar, right? Kumar, yeah. Mahfud Raji. Ipoh. Yes, Ipoh. Yeah. BU. Where's the BU? I think for another batch of student, right? BU. I think BU third year. It's not under Kuching or something like that. So I think they're coming from other batch. But it's okay to join here. Here, BU, so here, right? Strange, how come you say BU, not KL? Not KL, BU. Narendran. For KL student, they have some KG, some kind of BU, something like this called KL. But for Ipoh and the rest of the region, it's quite clear. It's IP or JB, something quite clear. But for KL, we have multiple region here. And now Ipoh. Bismaratan. Okay. Lexman Kumar KL. Here. Okay. Okay. ET, ever done, right? Yeah. ET. It's okay. Sometimes if you type outside here, some student in the previous what is this? Free meeting now. Probably they. How come we have 3 sessions for the same the same tutorial 2? 3 sessions never happened before. Strange. That's why it confused. Sometimes they join the wrong class. How to overcome this problem? I think it's quite clear. Tutorial 1, tutorial 2, tutorial 3, right? Quite clear. How come they split the three meetings? I'm sure this one, many people here. How come they split the 3? No idea. But, the most important thing is I need to keep the recorder on, so that for those who couldn't make it today, they can refer to the video later on. This is the most important part. Okay, let's come back to our tutorial 3. Okay, tutorial 3 is another word actually. Previously, we only look at the DC circuit, right? You know, in the electric circuit in the human world, we have a female and male, right? Female and male, they are quite two different species, right? Usually, they work differently, right? They are how they think also differently. But when it comes to the circuit, we also have AC and DC, right? DC usually powered by something like a battery. We have the symbol like this, right? Like 3 volt, or sometimes the symbol is in the circle form, plus minus 3 volt. It's a same thing, right? Same thing. Sometimes they just draw the battery. But this is for the primary school. For primary school, they just draw the battery plus minus, right? But for the engineering, usually we use these two symbols only, right? Usually we use this symbol or this symbol for the voltage source, right? For DC. For the AC, usually we only see this something like this, right? A circle with something looks like worms inside here. Okay. For AC, you cannot just say it's 3 volt. It's not enough. 3 volt is not enough. Okay. Usually, what we need to indicate here is the voltage source and the frequency. Because when it comes to AC, we involve the frequency parameter actually. So, for example, for Malaysia, the power coming from out from our wall socket from the TMB is AC, right? As you know, it's not DC. It's a 240 volt V. Actually, it's RMS. We'll talk about this later. RMS, and then the frequency for Malaysia is 50 hertz. This for Malaysia, and then for Singapore. You know, Malaysia is follow the UK standard, right? Singapore almost also follow the UK. Singapore is a 230 RMS, right? And then 60 hertz. And then for China, I remember China is a 220. That's why when you buy sometimes you buy those China electrical appliances, sometimes they are designed for 220 only. So for Malaysia, it's slightly 20 volt higher than China. Even though you go to Singapore, you buy their appliances, it's 10 volt less than the Malaysia. So that most of the time it won't last longer in Malaysia because our voltage is higher. It puts some stress on the component actually. Okay, back to the fundamentals. For the AC, you need to indicate the voltage and the frequency. Frequency equal to 50 hertz, right? When you back to the physics class, we can convert the frequency to time. Time is equal to 1 over frequency, right? The reciprocal of the frequency, we call the reciprocal. 1 over f is equal to the frequency, 0.02 second, right? 1 over 50, 0.02 second. You can convert from here to here, here to here. So the time, the frequency is equal to 1 over time, 1 over 0.02. You also get 50, right? 50 hertz. So this is really important from F to T and from T to F. Okay, this is something about the AC. When you look at the real topics today, for this unit 3, we look at AC. Unit 1 and Unit 2, we look at DC. So you need to see the difference here. The way how they analyze the things is really different. So why I think most of the students they can't see the main difference between AC and DC. You see in a DC circuit here, we cover in the unit 1 and 2. In a DC circuit here, let's say you have one capacitor. Let's say this is a voltage, right? You have one capacitor, and then you can see that the current can flow through, right? Sometimes we have resistance here, the wire. When the current, when the this current charging this capacitor, in this way it's charging, right? It's charging. When the charge full, when the capacitor is fully charged by a battery, it's become an open circuit. After it fully charged, it becomes open circuit. Okay, the circuit becomes something like open already. After it's fully charged. Okay, after fully charged, it becomes open circuit here. But for the AC here, this is a DC. For the AC, the thing is quite different actually. For the AC, oh, we are experiencing the network problem now. For the AC here, the capacitor will behave differently actually. How different it actually is it? Because AC we have this waveform going positive, negative, right? Because the power this power generated out from the generator, when the thing rotates, we got the south pole and north pole. South pole, north pole, and south pole, north pole. They are turning, right? They are rotating. So we have this kind of behavior because we have some kind of frequency parameter. We have this behavior we apply to this capacitor. This capacitor will behave something like a resistor. You'll behave something like a resistor. This one will become like something like this. Okay, but we won't call it a resistor lah. You're really confused. We call it a reactant. We call it an XC. Okay. When it comes to equation, it appear like this: 2 pi frequency component 2 times pi times frequency component times the capacitance is equal to the reactant. So reactant is some kind of a resistance. You can say that it's some kind of resistance, but this resistance is only appear when this capacitor in the AC environment. That's why you can say that the things become complicated now. When we introduce this frequency component, the thing will become very messy actually. You can look at this like by yourself right now. Okay, and to describe this AC, I think you need to understand what is sine wave. First, you need to understand what is sine wave. Most of the time we will use a sine wave or cosine, but most of the time it's sine wave. So let me do a bit of quick review. Sine wave starts from the 0 here, and then you reach the maximum point here, right? And then you go back to the 0 again. Here we call it a 0 crossing, and then you go back to the negative, same magnitude, and then you return back to the 0 again. And then you will repeat again, of course, you will repeat again, right? So in Malaysia, our frequency is 50 Hertz. It means in 1 second, you repeat 50 times the repetition rate. The repetition rate is the 50. That means in 1 second, we can see this cycle 50 times. So here is considered one complete cycle from here. If here is the starting point, the next starting point is here. So you can say that from here to here is one cycle. Sometimes we call this a one period. One period or one cycle. Okay? And then usually we're using the sine wave because sine wave start from 0. The cosine wave start from the here. This is a cosine wave looks like, right? But sine wave looks like this. And then here, the maximum here is our, we call the amplitude. So here we can say this is the maximum voltage here, okay? And then as an engineering student, you need to be able to name this waveform here as a, let's say the x-axis is a time, is a t in time domain, and then this waveform would be function of time is equal to the V maximum times sine omega t here, frequency component, right? Omega t. So this is how we name the sine form. We name this sine waveform. Okay, I think for this you can use this website here. I'm going to introduce one website here. It's called the Cyber Symbolic Graphing. You come to this website here. Let me show a few fundamentals. First, you can type the function t equal to, you type the sine. So this is a sine function, right? You can see, you can tell it starts from a 0. Here's a 0 point, right? The intersection here, 0, 0, right? You start from here. And then right now, the maximum here is a 1, only 1. Okay? So if we put phi in front of the sine, that means we define the magnitude to be phi and negative phi. Okay, this is the Vm, we call Vm here. This is Vm. Is any number in front of the sine function is an amplitude, actually. It's amplitude. So how about you have something like this? Ft equal to Vm sine theta minus 30 degree. What is this minus 30 degree actually? Minus 30 degree is some kind of the delay. So if you take this one sine t minus 30, you can see the delay, right? It's delay 30 degree here. Something like somehow delay, right? Let me change it to degree. Sometimes it won't you can see somehow delay right here, 30 degree. So if I want to delay all the way to 90 degree here, I change to 90 degree, delay 90 degree. Sometimes you just disappear. I don't know. Sometimes I don't know. On some computer it works just work very nicely. So here is a 90 degree here. Okay, here's 90 degree. So the delay from here, delay to this point here, here's 90 degree. Okay, here's 190. Then the peak here become 180 degree. Here's 180 degree. Here, this point. This point is 180 degree. Right? Here's a 90 degree. Here's a 0 degree, right? If you put 0, so you need to wait for a while sometime. So then you just disappear. Yeah, here's 0, right? So if you say minus 0, nothing, right? But sometimes you refuse to draw the waveform. Okay, you get my point. Let me do a quick summary. So for Malaysia is usually for layman term, layman just say Malaysia is a 240 volt, right? For layman, Malaysia is AC, right? For layman, they just write VAC, right? And then most of the people know that Malaysia is the 50 hertz. So when you want to put this on the graph in Malaysia, it should be like this. 50 hertz is equal to frequency, right? So if we convert to time, 1/50 is equal to 0.02. So in Malaysia, one cycle here, one complete cycle from the starting point to the end point here is called one period. Okay, and then t is equal to 0.02 second. So here in the center here is 0.01, and then at this point here is 0.02 for Malaysia. Okay, and then how about the peak? The peak in Malaysia here, the we call the VM or VP. We pick P for peak, right? So this is the RMS actually. This is the RMS value. For now, you just remember it's RMS. Later, I'll explain it to you. For you want to convert RMS to the V maximum, usually you need to multiply by the square root of 2. You multiply by square root of 2, which is 240 multiplied by 1.414, right? And then you get about 339 volt. So in Malaysia, the maximum voltage here we can arrive here is a 339 volt. Okay, so it's not 240 volt maximum, it's a 339 volt. Okay, you need to multiply by the square root of 2 to convert from the RMS to the V peak here. Okay, so when you want to write down the function here for Malaysia should be 339, right? And then sine, and then 2 pi f, right? 2 pi f. So what is 2 pi f? 2 pi f is 2 times the pi times the frequency. If you multiply by the you multiply these three together, 2 times pi. Oh, where's the pi? 2 times pi times 50. So you get 314. So here in Malaysia, the function should be right like this. 314, right? 314T. This is Malaysia. Okay, 314T. And volt. Okay, depend on what time you put in here, right? What time you put in here, you can calculate the voltage here. The voltage as a function of time is equal to 339 coming from here, sine 2 pi f, 2 pi frequency 314T. Okay, if we have any like minus 30, minus 90, that means this one will delay until here. This is called the lagging. We call the lag, like the turbo lag, right? Lagging. It should start from here, but it starts from here. It should start from here actually, but instead it starts from here. It's called the lagging, right? Some kind of delay by 90 degrees. So we should write this. We should write this one as this dotted one as Vt, voltage in a function of time, 339 the maximum voltage, sine 314T minus 90 degree. To express this waveform here. Okay, so when you come back to here again, I hope now you understand what's the meaning of Vt, Vm, cosine. Cosine start from the if you go back to the program again, cosine start from T. Phi is the amplitude, right? Cosine, you see cosine start from here. That's why we seldom use a cosine. We use a sine actually. Sine start from the 0. Cosine start from the maximum here. Okay. And then plus data, they mean they move forward. Plus data actually move forward. So if you say plus, now I say cosine t plus 30. You can see this one will move slightly to this direction, right? Slightly towards the left. So from here to here, let me cut and show you here. What it means is, this is the center point, right? This is the center point. Oh, from here to here is 30 degree plus 30 degree to the left. That means this is the future. This is the past. This is the future. So you shift plus 30 to the left hand side here. You can see here plus. If you plus 90, you're going to move further left. If you plus 90, so you'll move further left here. Plus 90, plus 80, plus 180 will move to this point here. If you plus 180, so you move to this point here. 0 is this point, right? 180 is this point. So you move to the left hand side here. So here's a bit confused. Here it's really moved to the right hand side, is a bit confused. It should move to the left actually. Okay. So sometimes these things are really confused. If you remember wrongly, then you will have trouble understanding all this. Okay, of course we can convert from sine to cosine. From sine to cosine, from cosine to sine, we just take a minus sign here. You can look at one example here. You see, we got one voltage source is a minus kind of voltage source, negative voltage source cosine plus 40. This is a frequency component, right? This is a frequency component, 2 pi f frequency component plus 40. Another one is the positive voltage here, positive voltage phi, by using the sine function is minus 50. So you want you to find which one is leading which one, which voltage is leading which voltage. So what do you mean by leading? Leading means is ahead of the voltage. This can be quite confusing sometimes. So if you refer to the graph, here's 0. Here is the time passing by. So time passing 1 second or time passing 2 seconds. This is in the past, right? Let's say you are here. Here means you already passed 2 seconds. Here's 0, your starting point. So here's consider the past. Here's the future. So the graph should be moving from the left to the right. On oscilloscope, the graph should be moving from the left to the right. Let's say at this point, after 1 second later, this point become here, right? This 1t, 2t, 1 second, 2 seconds, right? So when you have this one waveform like this, okay, another waveform is like this. So this one should be delayed, right? Let's say this is a V1, this is a V2. So V1 leads V2. V1 is ahead of V2. Here is the future. Here's the past. This is already past. So here just appear. This here appear late before. This V2 appear 1 second before. This one just appear. So this one V2 lead V1. And when you come back to the question here, one is the cosine, one is the sine. You can't just see which one lead which one unless we convert this cosine to the sine by adding the negative 90 here. we add a negative 90 to this 40 here, we get minus 50. Okay, now we can compare sine to sine function. Now one is a minus 15 to the future, one is a minus 50. Of course, this one is the V1 leads V2 leads V1. This only minus 15. This one minus 50. Okay, this is a bit confusing. V2 lead V1. This is minus only 15. I don't know whether this is correct or not actually. Sometimes they also make a mistake. So V2 lead V1. When you come back to the next topic here, you will see the waveform. Let me show you the waveform. Something right here. You can see now. I want to see the waveform, show the waveform. Wait a minute. I better use the online, okay? Better use online. Let's see the voltage leads the current waveform. You see the one, the voltage is the one on the left hand side. The current represented by this dotted line is on the right hand side, right? Then we say that voltage leads the current. Okay, voltage leads the current. Okay, and then plus is to the left. Sorry, plus is to the left hand side. Okay, let's come back to this again. Sometimes this can be really confusing, even though it's a straightforward plus and minus here. Let's come back to here again. Let me see this correct or not. Let me see. In order to understand this, sometimes you need to visualize by drawing a waveform here. If you draw a waveform, let me draw a waveform here down here to show you the try to visualize this. So let's draw the V1 first. V1 is 25, so the peak should be 25 here. Okay, so we start from minus. This is the original, right? Original start from 0, right? And then it start from negative 50. So negative 50 is in the future here. Wait. Negative should be in the. I think you remember. Negative should be delay. Delay. Let me confirm with this waveform again. Sometimes I'll mess up. Let's start with the T again. Let's start with T first. Okay, let's do a test right now. I 25 sine T minus 50. 25 sine T minus 50. I want to see. So it moves to the left hand side. Minus is moved to the left hand side. Okay, the other one is function 50 sine minus 15 equal to 5 sine T minus 15. This color, purple color here, but it takes some time to draw some time. Oh, it's just disappeared. So this minus 15 is to move to the left hand side here, minus 50 and then minus 15. So you say that the V2 is lead V1 by 30. I think it should be V1 lead V2, not V2 lead V1. Because the one on the left hand side should be leading. According to the theory, the one on the left hand side should be leading. See the one on the left hand side, the V lead the current. Voltage lead current by this angle. Voltage is here, current is here. Okay, you lead the current. Voltage. Let me find the one with the. Yeah, here. Yeah, this not. We should find the one with the. Let me find a better one. Current lag the voltage. So the current here is after the current is more to the right hand side, right? So the one on the left is the voltage, the blue line indicated by the blue line here. So voltage lead current lag voltage. Another word in reverse is current lag the voltage, right? But so this, I think this is wrong already. This statement is wrong because minus 50 is more to the left hand side. So be voltage lead the V1 lead the V2. So every time you come here, you confuse me sometimes. Sometimes they do make a mistake, okay. But we better to refer to the standard here. What do we mean by lead? Lead means on the left hand side, right? If you refer to the most of the tutorial online, lead means more towards the left hand side. Okay, you can do some research later on. We don't want to spend too much time here. Okay. Basically, you just follow the fundamental stuff. Okay. Understand this. Understand what is plus. Understand what is minus. Minus is to the left, right? Plus is to the right. Plus means a delay. Plus means delay. One more time to strengthen our memory. Plus 50 means to the right here, right? To the right, move to the right. This is 0 point here to the right. Minus 50 is to the left. This point will move to the left, right? Hey, it's not changing. I think it's not changing. Let's use a 5 only. Yeah, now changing already. Let's use 5 better. You'll show me a bigger graph. Sometimes the response time here is really poor. It takes some time to appear. But when I use other PC, everything really smooth. Today I'm using a new PC here. I'm using another PC. You see, sometimes it just so plus is to the right hand side. If I change this one to minus, it should change to this point or move to the before the move to the negative side, right? But you take some time to change it. It's not perfect here. So I'm quite sure the plus is a lagging. Plus is lagging. Minus is the leading to the future. Sometimes we think that plus is toward this direction. This one is quite confusing. Unless every day you work on this one, then that's why you can remember really good after you spend some time on this one. Okay. Now let's go to the main component of this AC. First, we should understand what is a capacitance. Okay, capacitor is basically they are formed by two plates. These two plates they can store the charge. One is a positive charge, the other one is a negative charge, and then the total charge is equal to the capacitance times the voltage. So if you have higher voltage here, you can multiply by the capacitance here. The capacitance is usually defined by the how large the plate is right now. Okay, if you have the larger surface here, you have a higher capacitance. So the total charge equal to the capacitance times the voltage. More voltage will push more electron to the plate. And then here are the few very important equation associated with this capacitor. And then the capacitor current is defined by C divided by the change of voltage over change of time, dV/dt. The voltage, you must take the integration 1 over C I dt dt. This is the initial voltage. The initial voltage stored in the capacitor plus 1 over C integrate from T0 to T. Okay. And these are the two most fundamental you should remember. Another one is the total energy here. We can store in the capacitor is 0.5 times the capacitance times the V square is the total energy stored in the capacitor. These are the few frequently used equation you should remember. Okay. One is what? One is current. Current for the capacitor is equal to C dV/dt. Voltage of capacitor equal to 1 over C 0 to T, and then I take the current I and then dt. Okay, just remember these two. And then the total energy stored in the capacitor is a half times CV square. Okay, these three are the most important ones to remember. So in a DC circuit, capacitor can be treated as a just open circuit for DC circuit. But when it comes to AC, as I said earlier, you can capacitor will become like the resistance, some kind of resistance here. Here we got one example. You can see the you are given this current waveform. Initially 0, and then it's rising to 100 milliamp, and then it's constant, stay constant. Okay, so you need to find the calculate the voltage across. This is given is current, but we need to find the voltage from 2 to at t equal to 2 milliseconds and t equal to 5 milliseconds here. First, we need to find the equation. From 0 to 2 is based on this equation, right? 0 to 2, more than 2 is this equation. Sometimes students have difficulty understand why is it 50t. This is just a function of this curve here. Okay, 2 we get 100, 1 we should get 50, right? So the equation is 50 times the t. T is a 2. This one is usually I'll use this methods here. First, I'll locate the point here. Okay, when t equal to 0, I equal to 0 here. When t equal to 2, I equal to 100, right? 100. So what is in the center here? When t equal to 1, I should be 50, right? Because this is a linear. Excuse me. Because this line is quite linear. So I should be 50. So it looks like the t here is the 1 multiplied by the t, you get the 50. If t is 1, then you get 50. If t is 2, you get 100. That means t need to multiply by some kind of a number here. So the magic number here is 50. Because 1 plus times 50, you get 50 here. 2 times 50, you get 100 here. So the magic number here is 50. That's why this function is 50t. Here just constant, here just constant 100. So from 0 to t, we can express as 50t. Okay, for more than 2, it's just constant 100. So to calculate the v, we use back the equation there. V equal to 1 over c, integrate this current here, 50t. By integrating this 50t, we get 50t squared over 2, right? The integration. Okay, if you don't know, if you forget about all this, right, you can use back this Cybolab here. You can use the integration here to help you understand how to calculate this. Let me show you. You can use this something like integration of 50t. Okay, let's say you can find the solution for you. Equal to 25t squared, right? T squared. Wait a minute. 50t, right? 50t integrate 0 to 2. We can also insert 0 to 2 here actually. Let me use this one. Here's 0 to 2. Let's integrate this dt here, dt. Okay, I think this one can help you to come up the answer. So 100 here, 100. Here, 100. Right? So nowadays, students are really lucky. They can use all these online tools here to calculate the. You can ask you to show all the step here, show step, all the step how to calculate this until the 100 here. Answer. Okay, but the t, if the t is 100, if the t is 100, from t0 to t5, from 0 to 2 to 5, from 0 to 5, if for the t equal to 5 milliseconds, 0 to t is this function, 2 to 5 is just 100. Okay, you need to do separately, and then you come up with 400 millivolt. Okay. So you can, as you can see, you can use the tools here, the Cybolab, to help you understand this. Okay. It is another student. Okay. But sometimes this appears quite frequently in the test actually. they ask you to calculate the voltage based on the current waveform here. We'll move a bit faster, okay? For the capacitor in parallel, you can see now they are arranged in a parallel. You can just sum all the capacitance together using this formula. CEQ equal to C1 plus C2. They're just opposite of a resistor, right? In resistor, you cannot just do this. Resistor, you need to 1 over R, 1 over R2, right? 1 over REQ. For resistor, they are quite opposite. Okay, this one you can take a look yourself. And then this one you can practice also how to find the all the resistance. Well, in parallel is sum, but in parallel you need to use the formula here. When it's in series, you need to use the formula like this: 1 over something, right? Just put the 1 over everything. When you see the capacitor in series, okay, use your technique here. This is a really simple question. I think you can practice yourself. For the inductor is not storing the charge, unlike the capacitor. This one I need to explain to you a bit. Just now we talk about the capacitor, right? For the capacitor circuit, you have to imagine these two plates storing the charge. Okay, when they fully charged, then the current cannot flow through anymore. The current will stop. Well, current will become zero. The current will become zero if the charge is full. The plate is full of charge. Current will become zero. But for the inductor, the things behave quite differently. Inductor is a kind of a winding wire forming a loop, a loop. When you apply the current need to be a constant changing. If the current is constant, example like this is the time. If your current is constant, you try to measure the voltage here is equal to 0. Okay, in order to generate the voltage here out from this electromagnetic field, you know when the current passing through a wire will generate some kind of electromagnetic field, right? From physics, we know that when the current passing through a wire, you'll generate a magnetic field. And then with this concentrated kind of loops here, we can concentrate all the magnetic field here, right? But remember the voltage for the capacitor is equal to L di dt. The voltage across this L here, the current must be changing di dt. Sometimes we express as a di dt like this. So if the current doesn't change, let's say the current is 0 and the time is changing, you'll get the 0 volt. The current must be changing. That means the current cannot like this. The current must be rising or dropping. Okay, rising or falling. If the current is rising rapidly, then you get a very high voltage because the dVdt here is very high. The dVdt is a slope actually. Here's the di, here's the dt. So here's the di dt, right? So when the slope is very steep, this value is very large. Multiplied by this value, you can get a very high voltage here. So the voltage here is a result of the electromagnetic field. Here is the electric charge, electric field. So they are quite different. One is an electromagnetic field, one is just an electric field. Okay, and how they work is actually opposite. You see later on. Beside all these fundamental equation, I equal to I over T, okay, V equal to L di dt. Okay, where is the V equal to L di dt? Now here, V equal to L di dt. I equal to 1 over L integration of Vt. They are just opposite of capacitor if you compare with each other, right? They are just opposite. And the way how they behave also opposite. You can see the inductor in series is just a resistor. You can just sum all together. When the inductor is in parallel, you need to put 1 over for each value, right? So you can see that inductor very close to a resistor, opposite to the capacitor. Well, when come to the AC circuit, the capacitor and the inductor, they just opposite each other actually. They oppose each other. So what do I mean is why they're working differently, totally 180 degree different. Sometimes what happen in the practical field when it comes to the real world. Explain this one quickly. So in the real world, if we have this power supply starting from 0, just now we've seen this many times already. It starts from 0. If the circuit come with certain inductor, we call it the inductive load kind of circuit. You can see the voltage, the current will be slowing down, will be lagging. You can see the current here. You can see the current lagging. This is called the lagging, right? Delay. It's a delay. This delay usually due to the inductive load L, due to this inductive load, inductor load. Okay. So in order to correct this problem, we want to bring this one to 0 again. If we add a capacitor to the circuit, we can actually bring this one close to the 0, recover the lagging effect back to the normal in phase. This way they are all in phase. Where two are in phase, the circuit perform better sometimes. When two in phase, let's say this is a voltage, right? So if the current is in phase, you can see they start at the same point, they go to 0 at the same point. This one go to 0 later, this one go to 0 faster, right? This one go to 0 later. Okay, so we have in a short, in short, if we have the problem due to the inductive load, the thing lagging, and when it comes to the real world, the TMB will give you a penalty usually. They'll give you a fine if your factory got too much inductive load. Okay, they'll call the power factor. The power factor lagging due to inductive load in the AC motor, in the pump, AC pump. Okay, the only way you can correct this problem is adding the capacitor, because capacitor and this one they just work opposite each other. When adding the capacitor to the circuit, you can bring this one to the 0, to back to the normal in phase kind of power supply. That's why later on you will see that inductor and the capacitor they just work opposite actually. They are in nature they work opposite. When come to the solution, they also can we can use one to tackle the other one. Okay. And here this topic is about the root mean square. And the only thing you need to understand about this root mean square, let me see how the slide explain this to you. So the slide trying to explain to you is something too theory. It's too technical, too theory. But for the engineering student, you need to understand the fundamental of root mean square. Let me explain to you right now. So the fundamental of root mean square is something like this. let's say you have one DC DC voltage here at 5 volt, right? 5 volt. Let me draw something like this. 5 volt. Okay, and then the 5 volt appear again in a pulse kind of format here. This is the voltage here, 5 volt. Okay, so let's say here is 1, here is 2. So 50% of the time, this 50% of the time, right, is 5 volt. So you can say the average here, you can quickly conclude that with the VDC, the average voltage here is 2.5. Because half of the time is 5 volt, half of the time is 0 volt. So average 2.5. Average here, 2.5, right? So when you say 2.5, many people understand it, okay? But when you come to the waveform with the positive and negative, positive and then negative, just like AC. So half of the time is 5 volt, half of the time is negative 5 volt. Two portion, right? First portion is positive, the other portion is negative. So if you take this, you use the same formula here, we call the average voltage. The average voltage becomes 0 volt. Because one is 5 volt, the other one is negative 5 volt, so they cancel each other. You can imagine that for the first month, you make 5,000 ringgit. For the second month, you lost 5,000 ringgit. So average you make nothing. But if your meter you're showing the 0 volt to the normal people, they think that 0 means there's no electricity, right? 0 volt, no electricity. But actually there's a power inside the line. That's why the 0 volt cannot represent this one. The VDC cannot represent this AC kind of environment. So to solve this problem, we need to have another voltage. We call the RMS. So if you take the same thing here, phi and negative phi, if we take the phi, we square it, okay? And then this negative phi here, we also square it. You understand when you square, we take away the negative, right? When we square this phi, we take away the negative. So if we plus these two together, okay, and then we have this square root to cancel the square we put in here. And then we need to calculate the average here, we need the average, right? 1 over 2, right? This is 1, this is 2, right? We average these two, and then we can calculate what's the number you try to find now. 25 plus 25, and then divided by 2, and then we square it. We square root it. Where is square root? Where? Yeah, here, right? Then we get 5. Then answer is 5. That's why this phi is become the VRMS. 5 volt RMS voltage. This is why our AC line in Malaysia 240 volt is the RMS. It's not the DC, the RMS. Because this is roots, mean, and square. Roots, mean, square. That's why they use the name here, roots, mean, square. Okay, it's for the AC, because now we are dealing with AC. In this tutorial, we're dealing with AC. That's why you need to learn all this root, mean, square here. Okay, and for root, mean, square, when you are solving all this by theory, you'll come up with this square root of 2. The VRMS and the V is square root of 2. In short, let's say, let me do a better one. Let's say this is a waveform here, a perfect AC waveform. Let's say this is a sine function, right? Sine function. Let's say here is your maximum voltage here. We call it Vm. So the function here is a Vm sine theta, right? So if this is given as the VRMS is given as 240 watt in Malaysia, so the Vmax, if you work out using the integration, you work out from here 0 to this t here, Vm sine omega t. You work out everything. You will come up with the Vm is equal to square root of sorry. This one becomes square root of times the VRMS. We call it VRMS here. VRMS. So Vm equal to square root of 240. Okay, 240 is the RMS value of this waveform. So to calculate RMS value, I give you, because this is too technical, I don't want to confuse you right now. The RMS value is equal to, first we need to take the square root, okay, and then from 0 to t, Vm sine omega t, the whole thing here you need to square because of root mean root mean square. We need to square, right? So square, and then we need to put in the roots, 1 over 2 roots, okay, to calculate the root mean square. Square, roots, and the mean. Mean is 1 over t. Here, from here to here is 1 over t. From here to here is t. So the mean is 1 over t. Just now I used the value 2, right? So this is a formula to calculate this value, root mean square, for this sine wave. If you calculate all the way to the end, you will get the root mean square is equal to Vm over square root of 2. That means Vm is equal to VRMS times square root of 2. Vm is equal to root mean square times square root of 2. So at the end, you arrive at this value here. This value here. If you follow the root mean square, okay, root mean square. So it's pretty technical, okay. Okay, here's another example based on the waveform. We need to calculate the root mean square for this value, and then need to calculate the power. Okay, if the voltage is applied to the 10 volt load, 10 volt is our load, then calculate the power for this 10 ohm. First, we need to calculate the root mean square because this voltage is changing, and the first step here is to calculate to find out the function for this rising curve, and then this is the descending curve, right? One is the ascending, one is the descending, right? You need to find the function for these two first, and then this just repeating later on, right? So the rising is 3t. The rising here is quite straightforward here. Usually let's copy this. Usually the ascending one is easy to find out. In the math, 0, 0, 1 equal to 3. If it's 0, then it's 0. If it's 1, then it's 3. So the function should be, here's a t, right? Here's a t. Here is the value, the v. When t is 0, we get 0. When t is 1, we get a 3. So the function of v, or we can say the v is the voltage, right? The v function of time is equal to 3t. 3 times the time. If the time is 0, if the time is 0, then 3 times 0, we get the 0 here. If the time is 1, then 3 times 1, we get the 3, this point here. So for the ascending one, the Vt equal to 3t. This is a function. For the descending one, the things are not so straightforward. The thing appears as something minus something t. Something minus something t. Okay, we can work out this slowly. First, we see the 1 here. 1 is 3. 1 end up 3. When time is 1, the voltage is 3. When the time is 2, the voltage become 0. So it's opposite, right? Opposite with the one. When time is 1, 3. So the function is something, this one minus something t. In the mathematic, when the reverse, in this reverse curve, reverse slope, we call the reverse slope here, negative slope. The function is something like this, for negative slope. So the magic number here, if you put a 6 here, and then you put a 3 here, 3t, then you try, if t go to 1, 6 minus 3, 1 equal to 3. So matching this answer, right? 6 minus 3 times 1. If 6 minus 3 times 2, you get 0. 6 minus 6, you get 0. So the answer here, for this slope here, the Vt is equal to 6 minus 3t. Of course, you can go back to the technique you use in you learn in the secondary school. Something like this, right? The m equal to y2 minus y1, x2 minus x1, something like this one to find the slope. To find the slope, that's why you can end up with mx plus c, right? You can go back to all this you learn in the school, but sometimes you can just remember the format. For the negative slope, is something minus something t. For the positive slope, it's just something multiplied by the t. Okay, you can go back and test yourself. You can go back. You can do a test quickly. Do a test. Let's say you want to find this function. Like this. Let's say from here to here. 0 you get 2, and then 3 you get 0. You can try how to find this function. What minus what t. Okay, you can do a test yourself. Yeah, of course there are many tutorial also. Let me do a quick search. Slope formula. Let's try a negative slope. We are only dealing with the so this one something minus 3x, right? Negative slope here. You can refer to many techniques that they use. First, they find the slope. So this slope is something minus something x, right? You can say plus also lah. Actually, this is the m. This is the m. Mx plus c. Okay. So here, let me clarify this one more time. 6 minus 3t here is equal to, this is the m, this is the c. So if you refer to the formula mx plus c, the thing we learned in the secondary school, this m is here, 3, negative 3, negative 3, c is plus 6. So C is 6. Okay, you can review yourself. This one's quite easy. After you done this one, then you can come up with these two equation. From 0 to 1 is 3t, from 1 to 2 is 6 minus 3t. And then you can put these two into together, because to find the RMS, you need to calculate separately. One is 3t, one is 6 minus 3t. You need to square root it, and then you need to square it, and then you need to square root, and then the 1 over 2. 1 over 2 is the mean, right? Total time is here. One cycle is 2 over 2 seconds. So 1 over 2 put in front, and then a big bracket here, and then integrate these two functions you have. Each function you need to square the function, and then at the end you will come up with RMS. After you know the RMS, you just take the general equation, the power equal to v squared over r. So for the this RMS, we just use the RMS square over the r. Okay, basically it's just all the calculation, all the mathematics from the secondary school actually. All right, so the last topic here is something about the phasor. And this is, I think, is a new thing for many students, the phasor here. So why we need to learn about this phasor is because in the AC circuit, like this is really simple, because the R, sometimes we call this a pure resistance, pure R. When it's a pure R, the things become really simple. There's no lagging, there's no leading. The waveform will start from 0 and then go to 0 and up at 180 degree. Okay, when the thing is R, things can be really simple. You can just take the current equal to Vm over R. Everything just like DC. But when we introduce when we put in the L component, the L component will cause the current to lag. Current will lag the voltage by 90 degree. So pi is 180 degree divided by 2 is 180 degree. So what happens is when it comes to this is the R, right? This is the R. Sometimes it's quite confusing by looking at this thing here. The reason why we need to learn all these phasor, because now we are dealing with the circuit with L and C. One which can change the waveform, cause it to be lagging, and then the C will cause the voltage to be leading. That's why you can see the changing of this the angle. We need to, in order to deal with this changing of angle, we need to introduce a phasor, because phasor is a faster way to calculate. For example, let's say you have this one. Okay, you have this voltage here, represented by this the time domain here. Let's say this is a voltage, okay, and then let's say the current is for this inductive current. You can see it's lagging, right? It's some kind of lagging from this point to this point. So this current is something like some value, and then X lagging, right? Lagging is a plus certain degree, right? Plus certain degree. So in the short form, we can just write this one X lagging plus degree. So this is called a phasor. Okay, because later on we need to plus multiple current together. Some is Y, and then positive angle. Positive is here, right? It's this side. Because we have multiple current, sometimes we have the inductor current, sometimes the capacitor current. Capacitor current is a negative, right? Inductor current is positive, right? Sometimes we have this changing of angle here, but we need to add them together. That's why it's better to change them to this phasor form. Okay. That's why in this chapter we learn all this phasor form, like this 35 ampere at the angle of negative 110 degree. That means this one to be more to the left, right? This is called the phasor. Another way to convert the phasor is to convert to the rectangular form. Okay, this is a phasor. Okay, let's come back here again. So this reference line is 0. When the current is lagging, you can see this one is rising up, right? It's shift from 0 a bit, go a bit higher, and then we have the angle in between. Okay, this is called the positive angle. So we can express this one as the absolute value of the current at this angle. For example, 15A at 45 degree. So like this, something like this. So if something they say they got 35 ampere at 45 degree, what it means is you can imagine something like this. This is a 0. You have to imagine something like this. It go up at 45 degree, and then the length here is the magnitude. The magnitude here is 35. Okay. So if the magnitude is a 50, then the thing becomes longer. 50 is a longer. The line when the line longer, it designates is a higher magnitude, 50 ampere, but still at 45 degree. So this one you can express as 50 at 45 degree. So when the angle is going negative, going the clockwise, this 45 degrees is a negative, right? Negative clockwise. So let's say the length here is 30 ampere. So it's a 30 ampere minus 45 degree, going negative. Okay, this is how we convert from the one form to another. And then actually when on the radar screen, actually they use this format to tell you how fast the airplane is coming, how fast their distance apart. Then on the airplane, on the radar screen, if you go to airline, radar screen, you can see the airplane is coming this way, right? Sometimes they have a very longer tail. When the tail is longer, that means the plane is very fast. When the tail is very short, that means that the plane is very slow. They can use this like this, the magnitude here, magnitude, and then the angle also. And then very quickly they can come out the whether these two are going to be correct together or not. They can determine, they can quickly come out the result by convert to this phasor form here. Okay, so V and I also the same thing here. So let's say the circuit is a pure resistive 35 volt at 0 degree is all the way on the horizontal line. It's all laying on the 0 degree here. This is for the pure resistance. Okay, so the way to express this one is 35.4 is the magnitude 35.4 volt at 0 degree. Okay, this is for the pure resistance. Okay, and this one will we need to touch something called the complex number here. I think this is the first time you see the complex number probably. So the complex number, we have one called the real number. The other one is called the imaginary number. Okay, so the complex number, why they call this imaginary, you can go to YouTube and then find out. Okay, but I give you a short one is in the complex number, when the 1 minus 1 square root, usually the 1 square root will get the positive 1, right? But the complex number will still get a negative. That's why they treat it as a negative. Sorry, they treat it as an imaginary number. They said that this number is something you have to imagine, because we cannot express it now clearly on the paper. You need to imagine this number. They call it imagine number. Okay, and then this imagine number, complex number, is something we call the rectangular form. You see, just now when we touch a phasor, this is the form we call the phasor form, right? Another name is called the polar form, because here's a degree. That's why they call this a polar. You can also convert this one to the rectangular form. It's something like the complex number a plus imaginary number b. So to convert here, you need to find the total r, the total length of this r, using the cosine and the sine function. Back to the here. Here's the total r. Here's the a. Here's the b. You look at this one here. The length here is a. A is on the real axis, so this is a real number, plus the imagined number is j here. So the distance for the j is b here, jb, yeah, right? Okay, and then the total length here, the r, is the total length. You can use this theorem. I think the Pythagorean theorem, right? There's a name called it Pythagorean theorem. Is equal to square root of a squared plus b squared. You take the a squared and the b squared, and then you put in the square root. You can calculate this length r. Because here's a 90 degree, right? You can calculate this r, and then if you take the r, of course you calculate this angle using the reverse tangent. Using the reverse tangent, b over a, b over the a, you can calculate this angle, right? Okay, and then if you take the a equals to r times cosine theta, b equal to r times the sine theta. This is all from the secondary school. A is equal to r times the cosine theta, because this is the adjacent, right? This is adjacent to this this length here. So r and a. So no, this adjacent. Sorry, this adjacent. R and a is adjacent here. So b is equal to r times sine theta. Okay, sine is because this one, b is directly facing this this angle here. So we use the sine. So the cosine is 1. I think this is called adjacent, right? This length is adjacent to the r. That's why using cosine. All this you learn in secondary school, right? You can review a bit here. And then we can convert the phasor form to the rectangular form. These two need to convert. Sometimes need to convert from here to here, here to here frequently. Okay, in order to calculate easily. Okay, because why we need to convert? Sometimes when we add them together, when we divide them together, polar form we can divide and multiply each other, right? But sometimes to add together, we should use the rectangular form. You can see here, when you try to add this number and this number, we can just add this negative 12 to this 23.5 if we convert to rectangular form. We can just add them up like this. But when you try to divide the thing, you better convert to polar form. You can see the example here. One number by one number here. Sometimes if you convert to polar form is better, right? This number divided by this number, you get 0.2, right? Okay, and then so to divide and multiply these two number, these two variable, is better to do it in the polar form, right? sometimes to add together, you need to convert to rectangular form. It's easier to get the result, right? You can see more example here. Every time you see the polar form, usually they are dividing actually or multiplying. Example here. All right. That's why the reason that we need to learn this polar and the rectangular form. Okay, and then the reason for them to be here is to because we are dealing with this AC circuit, we have this lagging and leading issue. We have this current and voltage that sometimes they are lagging, sometimes they are leading. That's why we need to have this form to have us easy to calculate the value. You can first look at this example. This is a very famous example. I think this one also in your assignment also. So we have these three different components here. They are in parallel, right? So if these three are resistor, they are very easy to calculate. But when we have this capacitor in the AC environment, inductor in this AC environment, these two will behave like some kind of resistance, right? But we are given a different name called a reactant. So you can see the reactant here for the capacitor is 1 over 2 pi f c. Okay, for the inductant is 2 pi f times the L. Okay, and then they introduce another variable called the G. The G is the reciprocal of R. 1 over R is called the G. Okay, because it's easier for them to write in another form here. G y equal to G. This is called the admittance. Y is equal to G plus JBC plus JBL. Okay, so the B, you need to take a reverse of this the thing here. Okay, let's put it in all in another form. Okay, I think right now you're quite confused. I know. First, you learned this R before, right? Now today we learn about something called the G. G is equal to 1 over R. It's a reciprocal of resistance. And then for the C, when C you apply you put the C in the AC environment, the frequency will make this one become a reactant, right? So the reactant here we call the XC. Reactant is called the XC here. R is still the R, but the under this impedance, we have a name called the impedance because now we are in the AC environment. The C becomes XC is 1 over 2 pi FC. Okay, and then the other name for this one is called the BC. BC is equal to 1 over XC, then become 2 pi FC. Yeah. Okay, and then for the L impedance is XL equal to 2 pi FL. 2 pi F, short form is omega, right? So for the BL is equal to 1 over XL, 1 over reciprocal, right? 1 over, so this one become 1 over 2 pi FL. Yeah, 1 over 2 pi FL. So to sum of the parallel circuit, the total resistance here, total resistance they call the Y, equal to G plus J BC minus JBL. This is minus because these two are opposite each other, right? One is positive, one is negative. This is a formula you need to remember. When it comes to the parallel circuit here, this is the total resistance, Y. They call it Y here. And then at the end, the impedance is equal to Z, right? impedance is equal to Z, and then Z is equal to 1 over Y. 1 over the reverse of Y becomes Z. Okay. This the thing. That's why the thing get really complicated when you reach this topic. Okay. Let me see. So this how to deal with this AC circuit. This all the formula I think you can slowly follow here. Like how to calculate the angle here. 1 over C minus IC over IL over IR. Here example. Let's see the when we put them in the series, in series and parallel. So here's a part series and part parallel, right? So the Z is an impedance R minus QC, so XC. R and C, they are in a series, right? Okay, this is a formula here. Sorry, this is a formula for the for this branch. And then for another branch, in the series here, the L is now become positive. Oh, wait, let's go back. These two are in series. These two are in series, right? R and C, R and L. You can see here, C, when they are in series, when this series, we have a negative sign here for this, we call the reactant, right? C. For the L, it's R plus JXL. This you need to pay attention to this polarity here when they are in series. Okay, and then the sum of all together, the sum of all, we use a Y, just sum them all together. This is they call the triangle. They call the triangle. One is the XC, one is the XL. So this is the resultant, the total. Okay, what it means like this. What it means like this, let me show you. Let's take this for example. So that you have one circuit in series, the R in series with the C is this YC here. So when you express this one actually expresses polar form is actually YC at this degree 34. Okay, so this is their magnitude here at 34 degree. Okay, another one is YL. YL is here, is at this negative degree. So YL is something at negative 29 degree, something at negative 39 degree. This one is the something at 34 degree. So the resultant here is to join them together, to join these two points together. To join these 2 points together, is a resultant. We call this one is a YT, the total. So in phasor form, you can just add them these two up. Okay, one is negative, one is a positive, and then the resultant you just add YC plus YL. In rectangular form, you can come out with the total. They call it admittance, the total resistance. Yeah, the total. Yeah, total admittance. There are so many names here. Admittance, reactant. Okay, here is asked you to find the total admittance only. The total admittance. Okay. Actually, the Y lah. The name is called the Y. Yeah. Total admittance. Okay. All this is just to remember. All this, you just need to take time to how to store this one in your brain. When you see when you see them in series, when you see them in parallel, this is how that looks like. One is the where is it? You see one is in negative form, right? Here, negative angle here. Negative meaning I think this all this all for this. There are so many things to cover actually. I don't think I have time to go into details in every slide to go to detail. But if you encounter any question, you can ask me lah. We can slowly tackle one by one. But to cover everything in details, we do not have sufficient time. Okay. And one more time, you don't have to worry about your assignment 1. As if you have done this one, then you have to wait for my video. I try to get it done tonight, okay? Because later afternoon I need to go out somewhere. When I come back tonight, I'll give you the hints for every question. Okay, so that you can double check your answer again. Make sure you are on the right track or not. Okay. Then if you are confident enough, then you can submit your assignment. I think the best time to submit is next week. Sometime next week you submit, then I can mark your assignment 1. For assignment 2, you can wait until we complete our next lab session. Then you can submit your. We complete our next lab session and plus the tutorial number 3. Then you can complete this question here. This is what we covered today, right? The impedance circuits. Okay. But this question, if I look at this question at a glance, is not so complicated. But for the beginner, you still need some tips also. Make sure you are on the right track. Okay. For this one, assignment 1 here, for the nodal and mesh analysis is quite okay. Only for the Thevenin, this part is quite tricky because the way how they orientate this how way they present this circuit actually you should rotate this one 90 degree. If you rotate 90 degree here become the 0 volt, and then probably the graph will look better. You know what I mean or not? If you rotate this one 90 degree here, like this, probably you feel confident after you rotate 90 degree. You see, rotate 90 degree. So here's 0 volt, here 60 volt, 30 volt. Here's your output. Sometimes you need to do this, okay? Here rotate 90 degree. So here's 0 volt here. Okay. Actually, I should prepare this one a few days earlier, but too bad this few days are too busy already and work. I'm too busy to come up with a video. So far, any question or not, guys? We are already past our time actually. You have any question you want to ask? Any question you want to ask? Otherwise, you tonight you wait for my video. I'm going to publish the video together with this tutorial 2 video lah. Everything I will post to the YouTube. Okay, and then you just take your time, go through the video. I'll split the video into each question. Like question 1, I got 1 video. Question 2, I got 1 video. So if you have any question, yeah, they kind of compress many topics into one actually. But it's still possible for you to learn actually. In the traditional way, we take 3 months to learn probably just unit 1 and unit 2 only. We take 3 months to learn unit 1 and unit 2. But this time you need to take 3 months to learn about 4 or 5 units. So you're a bit tricky lah actually. But don't worry too much actually, because I asked too many of my colleagues now. Many of my colleagues they are now in PhD already. Many of them are in doctor already. They get their doctorate already. I asked them lately. I say that do you when you first learning all this electric circuit all this Ohm's law, all this phasor, all this rectangular form, are you sure? Are you clear or not? When the day you first learning all this thing, all this topic, they also say they are very confused. The first time they read all this, they are already confused. I also recall that the time when I was student like you, when I first see all this, I also become really confused. What is the purpose of all this phasor? Why we need to learn all this Y, G, all these thing spatial symbol? Why not just use R? Why we need to convert R to G? At that time, I also quite confused. I don't know the purpose of doing that. Okay, that's why during this tutorial, I try to explain you all the purpose. Why you need to learn all these waveform? Why you learn all this phasor? Why AC is so complicated? Because we bring in the anchor, the frequency. We bring the frequency component, and then due to the capacitor and the inductor, they change the frequency. They change the anchor to cause to leading and lagging. And when something is in leading, something in lagging, you want to add them together. You need to have some kind of method to calculate, right? That's why the phasor. That's why they invented the phasor and the rectangular form to help us calculate all these value, leading and lagging in degree. I think you take some time for you to understand all this. You're not so immediate. You can understand 100%. Probably today you get 20%. Probably a week later you get 30% already, 20 or 30%. You take time to go through all this actually, because as I told you, for every new student when they first see all these things, most of them are confused because they are totally out of this world. in our daily life, we never encounter all these Y and G or this thing, right? Suddenly you learn all these things. Okay, so I take your advice, your suggestion. Include the flow or steps what after each question. Okay. When I post a question later on tonight, late tonight lah, not early tonight, very late tonight, probably close to 12 a.m. When I post a question, probably if you have any doubts or any question, you also can post a question on the YouTube comments area. You put a question on the YouTube's comment area. I try to answer your question. Okay, and then when you are done, you can just submit to the assignment. Okay, you don't need to worry about the late or the over the due date anything. As I said earlier on, for the past semester, CC allowed you to submit even though it's over the due date. So for those who already submitted, you can request for resubmission. It's not a issue actually. There's a request for resubmission button you can press, okay, to request for resubmission. I think the CC will just grant you the request. Okay, guys, I think to move on to my next schedule. So I'll stop it here, right here. Okay, anyone? You have any question before we left? Okay.
Okay,
thank you
sir.
guys
Thank
for
you,
your
sir.
attention. Okay. So we'll still keep in touch. From now until the 28, right? And remember that the next time we meet, will be on the 28th. Sorry, 20th. The next time we met will be after the Chinese New Year, 20th of February. 2 weeks later. 2 weeks later, we're going to meet again. But hopefully, before the Chinese New Year, hopefully before the Chinese New Year, you can submit. I think the best time to do that is before the Chinese New Year. You submit your assignment number 1. That's why, and from now until the Chinese New Year, 13, we still have about 6 days something. 6 days. I think if I post you some hints, probably you can answer it right away. So yeah, I think you still have sufficient time for you to complete assignment 1. Okay, guys, I don't want to talk too much. Okay. All right. Happy New Year. Okay. Happy holiday, everyone. I see you back in 2 weeks. 2 weeks time. Okay. In 2 weeks time, I see you back. Okay. Bye bye.